Hello friends, where I welcome you all in a series of lectures of generation of microwave signals under the topic microwave and radar engineering, which is there in the syllabus of Mumbai University for their 7th semester. So it is useful for all engineering students including Mumbai University. So in my series lecture I will give you an idea about the generation of microwave signal, that is how the microwave signals are generated. So this is my first lecture. I myself Mrs. Vandana Sawant, working in a SIS Graduate School of Technology. So this lecture will be useful for all engineering college students. First we will see what are the different devices that can be used for generation of this microwave signal. Basically microwave signals are the high frequency signals. So for the generation of a high frequency signal, normal devices which are used, that are for the low power signals we can use in a solid state devices, and for high power signals we can use in a conventional tubes like triodes, tetrodes, pentodes, etc. But since triode, tetrode, pentodes, they are having some limitations. If we are using these devices for higher frequencies, more than 1 gigahertz, these devices fail to operate. First, before going to a microwave signal generation, we will see why these devices cannot be used, why these conventional devices cannot be used, then how we can modify these conventional devices to generate a microwave signal, that we'll see in the following lectures. So basically if you see the structure of these conventional tubes, it consists of filament, cathode, grid and plate. This is the structure of this conventional tube. So filament and cathode are used to generate the electron or electron beam. The grid is always having a positive AC signal, so it is used to accelerate these electrons, and the electrons which are accelerated are collected by the plate. So this is a basic structure and working of this conventional tubes. But if you want to use this tube at a higher frequency, what happens? See, if the frequency rises, there are certain effects takes place. These are called electron transit time effect at a higher frequencies. Second one is a parasitic effect. Third one is a conductor loss due to the skin effect, radiation loss, dielectric loss, charging current loss. Now we will see one by one. That is electron transit time effect. That is a very big limitation for at a high frequencies, and parasitic effect also. So we will see this in detail afterwards. But before that we will start with this losses. Like parasitic effect means what? That is at a high frequency lead inductance as well as inter-electrode capacitance goes on increasing. So we know that as the inductance increases, reactance increases, but as the capacitance increases, reactance decreases. This situation at a higher frequencies, that is called as parasitic effect. Now this parasitic effects is limits on the operation of power in the at a higher frequency. So we will again see this parasitic effect later on in detail, what are the different capacitance or lead inductances and how it is affecting, but this is for your knowledge. Then second one is the conductor loss. Now see, as we know that the frequency increases, the frequency increase in a frequency is, that is conductance is directly proportional to the square of frequency. So as the frequency increases, the conductance increases. Conductance means the reverse of resistance. So as the conductance increases, resistance decreases, and this decrease in resistance create a shorts in the circuits, and that will loss of power. So this is called as a conductor, and conductors are everywhere. Without conductors we can't have any device. So this loss due to the conductor will takes place at a higher frequencies, and that is great have an affect the operation of a device. Second one is a radiation loss. We know that as the frequency increases, the chances of radiation goes on increasing. If we are having the frequencies in a gigahertz range, then the radiation loss is more. Radiation takes place, and the loss of power due to the radiation is called as a radiation loss. Then next one is a dielectric loss. So in the dielectric loss, that is, we are using the devices, with inside the device we are using a dielectric material. So whatever the loss inside in this material, that is called as a dielectric loss. Then that is charging current losses. So whenever we are using a dielectric material, then the leads, all these creates a capacitances in the circuits at a high frequencies. Now wherever the capacitance is present, we need to charge this capacitance for a transit time. So this, whatever the power wasted in a charging these capacitances, that is called as a charging current loss. So conductor loss, that is the penetration of the signal in the direction of propagation, that is the skein effect will takes place and the conductor loss will takes place. Then the radiation loss, dielectric loss and charging current loss. These are the limitations for a high frequency. Along with this, other limitations are electron transit time effect and parasitic effect. So we will see these two in detail, as these two are the main culprits for which are limiting the use of these conventional tubes at a higher frequencies. So we will see these two in detail. So electron transit time effect. First we will see transit time effect. Then before going to the transit time effect, first we will see what is the transit time. Transit time means the time required for an electron to pass from or to move from this cathode to the grid. So that time is called as transit time. That time is called as transit time. So if that transit time is quite large, then what happens as compared to the time of the AC signal which is present inside this, which is present on this grid. So that we will see. Okay. Now see, first of all we will see the normal operation of this device. This is a triode. Then here the electron gun is there. So electron gun hits the cathode. So the cathode will emit the electrons. These electrons will, as the grid is having a positive voltage, if the grid is having a positive voltage, the electrons will get attracted towards the grid. They will pass from the grid and they will get accelerated by the grid and they will reach to the plate. Now this plate is there that will collect the electron, and because of these electrons are collected at a plate, the signal will move from the output terminal. Signal will move to the output terminal. This is the normal operation. But see, at a high frequency what happens? See, at a lower frequency we can say that is electrons, when the electrons are emitted from the cathode, there is a positive half cycle on a grid. So because of that, when the electron reaches to the grid, electrons get attracted to the grid, they reach to the grid, they will experience a positive voltage on a grid, they will get accelerated and they will reach to the plate. So this is for the lower frequency, and for the lower frequency this positive voltage on a grid will remain for a longer time, because at a lower frequency time period is more. So the electrons will get a time from travel from cathode to the grid, and they will get accelerated from a grid towards the plate. But if this frequency increases above 1 gigahertz, then if this frequency increases above 1 gigahertz, then what will happen on a grid? The 1 gigahertz is having a time period in nanoseconds. So on a grid, the positive voltage will be remain for a very small time. Then immediately there will be the change to the negative, then again negative to positive, positive to negative. That change in a voltage on a grid will be very fast. So in that case what happens, that is whatever the electrons emitted by this cathode, they will reach to the grid. By the time electron reaches to the grid, if there is a positive half cycle, then the grid will be positive, electrons will get accelerated and they will reach to the plate. They will reach to the plate, and the outputs, we will get a fair output signal. Okay, but what happens if the electrons are emitted and by that time from the cathode, and by that time the grid voltage changes to negative? If the grid voltage changes to negative, the grid is itself is a negative, so it will not accelerate the electrons. What it will do, it will reflect the electron. Because of the negative voltage, electrons which are reaching to the grid are reflected back towards the cathode. So as the electrons get reflected back towards the cathode, cathode is also negative, it is not going to catch that electrons, it will reflect that electron again back towards the grid. Then also at the grid, in this position, in this case, if again there is a negative voltage on the grid, same electrons will get again reflected back to the cathode, and again cathode will again reflect it to grid. So in this case, the electrons, when there is negative voltage on a grid, the electrons will only oscillate in between the grid and cathode. They are not going to reach to the plate. So as they are not going to reach to the plate, there is no output signal, or there is a great reduction in the efficiency of this output signal. So that is called as a transit time effect. That is the transit time, that is time taken by an electron to reach to the grid, is less than the fraction of less than the AC signal that is positive half cycle time period of positive half cycle of this AC signal. So that is called as a transit time effect. Actually, to have a proper operation, the time taken by an electron should be equal to the fraction of the time of the AC cycle, AC signal. So time period of a fraction of time period of an AC signal. So that is not happening over here at a higher frequencies. So because of that, the electrons will oscillate in between the grid and cathode, and there is a great reduction in the output voltage or output power. So that will reduce the efficiency of the device at a higher frequency, and that is called as a transit time effect. Now we'll see the next effect, that is a parasitic effect. Parasitic effect means what? There is a, whenever we are using any device at a higher frequencies, there will be the many capacitance will get generated. That is the inter-electrode capacitance. We can call it as an inter-electrode capacitance. And again there is a lead inductance is also there. So inter-electrode capacitance and lead inductance. So lead inductance, as we increase the frequency, lead inductance goes on increasing. Inductance goes on increasing, that means reactance goes on increasing. And again the capacitance goes on increasing, means the reactance goes on decreasing. Now the reactances of this actual device will be get comparable to the reactance of this LC circuit. So LC circuit, then you will say why we need an LC circuit. We always require to generate a high power signal, we always require to have a one tank circuit at an output side, so that it will create an oscillations and the output power goes on increasing. So this whatever the reactance, that will get be comparable to this outer LC tank circuit. So because of that, what happens, the reactance here, as a frequency increases, reactance goes on decreasing, and one point will come, the reactance will act as the things will come, that is whatever the resistance of the device, that will equal to 0, and the device will act as in a short circuit, and the signal is given to the leads only. So it will not reach to the tank circuit. So no output power or no oscillations will take place, and it will load the tank circuit and no oscillations will take place, and there is no increase in output power of the device. So that is called as a parasitic effect. So any tube, any type of tube, conventional tube, if we are going to use it, then these two effects are very very limiting, creates a very high limitations on the operation of a tube. Then what to do? Then the scientists thought like that, we can't change the structure of a tube, but we can use these limitations in a such a way that they will turn into the advantages at a highest frequencies. So the scientists have stated some principle for generation of microwave signals, and by applying these principles on conventional tubes, we can make this conventional tube to be used as a for the generation of a microwave signal. So what are these principles? The first thing is that what is the transit time effect that can be used more intelligent way. That means the transit time effect can be put to an advantage. So this is the first rule to work this conventional tube as a microwave tube, and that is called principles of microwave tube. Second thing is that now to work this transit time effect as a more advantage and get a highest output power, they have decided on a second principle like that transfer of power from a DC voltage to the AC microwave signal can be done by using two processes. One is called acceleration of electrons in the DC electric field and the deceleration of electrons in the AC electric field. So as a result of acceleration and the deceleration of electrons, we can transfer the power from a DC voltage supply to the microwave source of the AC voltage or AC microwave voltage. So this can be achieved by changing some operational factors in the conventional tubes. Now whenever the deceleration takes place, then what happens? The velocity of electron decreases. As the velocity decreases means electron loses their kinetic energy. Now once the energy is lost, it should be catched by someone because energy should be constant. So this loss of kinetic energy of electrons is gained by the AC voltage which is present or AC electric field which is generated at a microwave frequency. So the strength of this AC electric field goes on increasing and we can get at an output side good strength or high power microwave signal. So these principles are implemented in the tube, so that conventional tube, so that they can be used as a generation of a microwave signals. Now this how we can change the structure or how we can use this transit time effect or loss kinetic energy effect in a more advantageous way for generation of a microwave source, that we will see in our lecture number 2. There are many microwave sources are available like reflex klystron, TWTs, magnetron, CFA, backward wave oscillator. So all these type of devices are work on these principles only. So this principle, how they will work on this principle and generates a microwave source, that we will see in our series, in this series of lectures. So second lecture will be devoted to the generation of a microwave signal by using a reflex klystron. How? Then in that we will see how more intelligent way these effects will be turned or can be used to the advantages. Thank you.